When you're dealing with data, there's this constant tug of war happening. On one side, you've got this dream of perfect, pristine organization. And on the other, you've got the need for raw, blistering speed. So, which one wins? Well, as we're about to find out, the real answer is a whole lot more interesting than just picking a side.
I want you to imagine walking into a library where books are just thrown into giant piles. Seriously, no sections, no catalog, just total chaos. Trying to find one specific fact would be an absolute nightmare, right? That's exactly what working with a messy database feels like. It's not just clunky, it can actually lead you down the wrong path.
And that brings up a pretty wild question. Can your data actually lie to you? And when it's this disorganized, oh yeah, it absolutely can. It starts to create all these little contradictions and inconsistencies that can point you toward conclusions that are just flat out wrong.
And these lies, they usually show up as three classic problems. We call them anomalies. First, you've got an insertion anomaly. This is where you literally can't add new info because some other totally unrelated piece of data is missing. Then there is the update anomaly. This is a sneaky one. You change a detail in one spot, but the old, wrong info is still hiding somewhere else. And maybe the worst of all is the deletion anomaly. That's when you delete one little thing, like an employee record, and you accidentally wipe out other critical information, like the entire history of a project. Each one of these is like a landmine just waiting to corrupt your data.
So how in the world do you even begin to fix this kind of chaos? Thankfully, we don't have to reinvent the wheel. Way back in the 1970s, a brilliant computer scientist named Edgar F. Codd came up with an amazing system for bringing logical order to all this data madness. And he called this whole process Database Normalization. Now it has two really critical goals. First, you want to get rid of redundant, duplicated information, saying the same thing over and over. And second, you want to improve data integrity, which is just a fancy way of saying we need to be able to trust that our data is accurate and reliable. And listen, this isn't just some random messy spring cleaning. Normalization is a very structured process. It follows this clear set of rules called normal forms, and they basically act as our step-by-step guide to getting a clean, logical database. Okay, so there are actually a bunch of these normal forms, and they can get pretty academic pretty fast. But the reality is, you get most of the bang for your buck from just the first three. So let's dive in and break those down. So, first normal form, or 1NF. This is the ground floor. It's the absolute foundation of everything. And the rule is super simple. Every single cell in your table has to be atomic. That just means it holds only one single piece of information. No lists, no comma-separated items stuffed into one box, just one value per cell. Period. Let's look at this example right here. See that subject column? It's got 3 different topics all jammed into one field. How on earth are you supposed to reliably search for all the books just about database? It would be a total mess. This table is a classic violation of first normal form. So what do? Simple. We break it apart. We make a totally separate table just for the subjects. And now each subject gets its own row. See? Every cell is atomic. This satisfies 1NF. The book is cleanly linked to 3 separate subject entries, and now the data is so much easier to work with. All right, on to the next rule. Second normal form, or 2NF. Now this rule really kicks in when your table's unique identifier, its key, is made up of more than one column. 2NF says that every other column in that table has to depend on the whole key, not just a piece of it. So check out this table. The key that makes each row unique is the combination of title times format, right? The price totally depends on both. The hardcover costs more than the ebook. But what about the author? Chad Russell is the author whether it's a hardcover or an ebook. The author only depends on the title part of the key. That's what we call a partial dependency, and it's a big no-no for 2NF. And you can probably guess the solution by now, right? We split the table again. We create a book table where the author correctly depends only on the title, and then we make a separate price table where the price correctly depends on that full combination of title and format. Now every piece of data is right where it should be. Finally, we hit third normal form, or 3NF. And there's this classic saying that just nails it. Every column must depend on the key, the whole key, and nothing but the key. That last part, nothing but the key, is all about squashing something called a transitive dependency. That's where a column that isn't a key depends on another column that also isn't a key. Look here, the primary key is the title. The author depends on the title, which is fine, but
The author nationality doesn't depend on the book's title, does it? Nope, it depends on the author. So you get this indirect chain. The title determines the author, and the author determines the nationality. That's a transitive dependency. To fix this, you'd move author nationality into its own authors table. Okay, hold on. We've just spent all this time breaking our data into these perfect, logical, tidy little tables. But in solving one problem, we've kind of created another one. All these tables are linked together. So what happens to all those connections if we need to delete something? How do we stop the whole system from falling apart? This is where we get two really powerful strategies. First, there's on-delete cascade. This creates a chain reaction. If you delete a parent record, it automatically deletes all the child records that depend on it. Think about deleting a customer's account and having all their old orders get deleted too. The other choice is on-delete set null. In this case, deleting the parent just orphans the child records. It sets their link to the parent to null, but it keeps their data. You do this if those child records could still exist on their own.
So, let's recap. Our database is beautiful. It's a work of art, a model of logical perfection. It's clean, there's zero redundancy, our data integrity is rock solid. But there's a pretty big catch. When you have to pull information that's spread out across all those different tables all at once, it can be, well, really slow.
And this quote just says it all perfectly. The practice of denormalization is a strategic time-space trade-off. We are consciously deciding to sacrifice some of that perfect structure and, yeah, use a little more storage space, all to gain a whole lot of speed when we need to read our data.
Let's make this super real with a classic example. Say you have a blog. In a perfect, normalized world, to get the number of comments on a post, you'd have to query the posts table and then join it to the comments table just to count the rows. It works, but it can be slow. The denormalized approach, you just add a comment count column right onto the post table itself. Now getting the count is instantaneous. Of course, the trade-off is that every single time a comment is added or deleted, you have to remember to update that number. You're trading a little more work on the write side for lightning-fast reads.
So where does that leave us? Are we supposed to go for pure, perfect normalization, or this messy but fast denormalization? Well, the truth is, modern database design isn't about picking a side. It's about becoming an expert at striking a delicate balance based on what you actually need.
The way the pros handle this is a really smart three-step process. 1. You always start by normalizing your design. Get it clean, get it logical, usually to 3NF. 2. You use profiling tools to find the actual performance bottlenecks in your app, which queries are really slowing things down. And 3. Only then do you go back and strategically denormalize just enough to solve that one specific problem. It's a surgical solution, not a sledgehammer.
And that really leaves us with the big question you have to ask yourself every time you design a system. What's the ultimate goal here? Are you building a pristine, perfectly cataloged library where every single fact has its one and only proper place? Or are you building a high-speed warehouse, optimized to get information out the door as fast as humanly possible? The true art of great data design is knowing exactly how to build a little bit of both. Thanks for digging into this with me.